Let us once again rewind the mechanism of hydration of an alkene. Now suppose we are taking HCl, it will ionize into H positive and Cl negative. Now H positive will be attacked by a molecule of water. We are using dilute acid, so there is excess amount of water in the medium. Now H positive on absorption with a water molecule forms H3O positive, that is hydronium ion. Now the pi bond will be shifting towards one of the H atoms, and simultaneously the OH bond takes over the oxygen atom. We get H2O and a carbocation. Now H2O is a good nucleophile, and again Cl negative is there. Cl negative is a far better nucleophile than H2O, but one thing here is that Cl negative is being surrounded by a large number of solvent molecules, that is water molecules, with their positive end pointing towards Cl negative, and weak ion dipole bonds are formed between Cl negative and a large number of water molecules, and this process is called solvation. And since water molecules are in excess in a dilute solution, the Cl negative, solvated Cl negative, will find it difficult to pierce through the large crowd of water molecules to attack the carbocation. So there is a chance of attack of the carbocation by Cl negative. And if the acid is, say, H2SO4, it will ionize as H positive, and H positive will combine with H2O, producing HCO positive, and here a carbocation again would be formed, and the corresponding anion, that is O negative H double bond O OH. That is one proton removed from H2SO4 give this anion. Now this negative charge is involved in resonance, in the sense the electron pair of oxygen negative is delocalized over the structure. So this oxygen becomes negative, and we can have a canonical structure, O double bond S, O negative, double bond O, then OH. Now again by shift of this pair of electron, this electron pair may be shifted in this direction, producing another canonical structure, S double bond O, O negative, and OH. So this is the bisulfate ion, which can be called a conjugate base. The bisulfate ion is stabilized by resonance, so that the negative charge over oxygen atoms will be partial, so it cannot function effectively as a nucleophile. So bisulfate ion, if the reaction is conducted in dilute sulfuric acid, bisulfate ion cannot act as a nucleophile. And again, even if it acts as a nucleophile, it has to pierce through the crowd of water molecules surrounding this carbocation. And again, water can act as a nucleophile, so that to the positive carbon, a lone pair of water is donated, and a positive carbon possesses a vacant orbital. So into this vacant orbital, this lone pair orbital donates its electron. So overlap between the lone pair orbital and vacant orbital of this carbon occurs. In this case, one electron is given to this carbon, and the charge is being carried over to oxygen, and we get OH2 positive. And OH2 positive is a good leaving group, so that another molecule of water acting as a base here establish the bond with this H, and this CH bond shifts in the direction, and OH 2 positive is removing as H2O by absorbing this pair of electron towards the oxygen, and so that this reaction is reversible in the sense this water molecule can act as a nucleophile. So this step is reversible because of the tendency of water to act as a nucleophile, and this OH2 positive can act as a leaving group by attack of a base. Here water molecule is acting as the base, and again Cl negative cannot act as a base, or a bisulfate cannot act as a base because of the fact that one of the reason is that Cl negative is less basic, because if Cl negative were more basic, then it would have combined with H positive to give undissociated HCl molecule in excess, but HCl is found to be a strong acid, so there is a lesser tendency for Cl negative to take up H positive. So Cl negative is less basic, we can say, and again its concentration is low when compared to the amount of water molecules present in the medium. So water itself is acting as the base, and if it is dilute sulfuric acid, again water is acting as the base because of the presence of water in excess. Bisulfate cannot act as the base. Then step 2 is the attack of water molecule as a nucleophile on the positive carbon, and again for the same reason the reaction is reversible, so that in the third step one H positive is removed from the structure by reaction with a water molecule acting as a base, and the third step is not shown here. There the H positive is taken up by H2O to produce H3O positive, and we get the free alcoholic group. So all these steps are reversible because of the fact that water can act as a nucleophile and again a base. So that is all about the mechanism of hydration of alkane. You have to study this mechanism because it is given in your text. Now the reversibility of steps is due to 1. the functioning of H2O as a nucleophile, and then the functioning of H2O as a base, and again H2O is acting as nucleophile and base in this reaction because of the excess amount of water present in the medium, because we are taking dilute acid. Now coming to another mechanism which you need not study, that is the reaction between acid and lithium aluminum hydride. Their first stage of the reaction, step of the reaction, is the reaction between H positive from acid and H negative from AlH4 negative to produce H2 gas, and then AlH3 absorbs a pair of electrons from O negative into its vacant orbital. Now aluminum compounds, just like boron compounds, are called Lewis acids because the valency shell of these elements, for example in the case of aluminum, the valency shell is 3s2 3p1, and it undergoes sp3 hybridization to get 4 hybrid orbitals and only 3 electrons, 3s2 3p1, 3 electrons, and 1 electron each will occupy 1 hybrid orbital each, so that 3 hybrid orbitals will contain 1 electron each, and the 4th hybrid orbital will be vacant, so that this 4th hybrid orbital can accept a pair of electron, and any species which can accept a pair of electron is called a Lewis acid. Here O negative provides a pair of electron, so that this lone pair orbital overlaps with the vacant orbital over aluminum, and we get OAl H3 negative. Then the further reactions occur, and we finally get the alcohol. So much about the reduction of acid to the alcohol. Now some conversions, that is convert propan 2-ol to propan 1-ol. Now this is propan 2-ol. You number the carbons 1, 2, 3, propan 2-ol, and this is propan 1-ol. Now we can convert the hydroxy compound to the halide by reaction with the PCl5 or SOCl2 or HCl and anhydrous chloride or even PCl3. Then it is reacted with alcoholic AOH. Removal of HCl from either direction can give only a single product. Now this can be converted to a primary alcohol by reaction with the diborane first, and then with the alkaline hydrogen peroxide you get the primary alcohol CH3, CH2, CH2OH. So that is a method for conversion of the 2-ol to 1-ol. Now then conversion of CH3OH to CH3CH2OH. This method, it is called ascending because one carbon atom is in excess in the product. Now to get one more carbon in this structure, we can use potassium cyanide as the reagent. For that you have to convert the alcohol into the corresponding chloride, alkyl halide, using PCl5, CH3OH, OH is replaced by Cl, and then potassium cyanide, Cl is replaced by Cn. Then hydrolysis in acid medium, cyanide is hydrolyzed to COOH, and then reduction using lithium aluminum hydride. The COOH group is getting converted to primary alcoholic group, that is CH2OH. So we can ascend the alcohol, can get the next higher homologue of the alcohol by such a sequence of steps. So two conversions. But lithium aluminum hydride is an expensive reagent, so another convenient method, economic method is used, that is conversion of the acid into its ester derivative by reaction with an alcohol in presence of acid as catalyst. So acid catalyzed esterification reaction, it is called. An acid reacts with alcohol, the OH group of acid combine with the H of alcohol, removing water, and we get CH3CO double bond O C2H5, that is the ester compound, and this is named as ethyl. Now ethyl group is obtained from the alcohol, so we call it the alcohol part. Then acetate part is obtained from acetic acid, and the ester is named ethyl acetate. Now acetates, ethyl acetate, acetates are generally pleasant smelling compound. Ethyl acetate is a pleasant smelling compound. Now esters are formed by the reaction between alcohols and acids catalyzed by an acid, and here a simple mechanism where the OH group of acid is involved. The lone pair of oxygen of the OH group is donated to the catalyst acid, so we get OH2 positive. OH2 positive is a good leaving group, so this bond will be shifting over oxygen atom, means the pair of electron in this bond will be taken up by the orbital of oxygen, so that the share of this carbon is obtained by this oxygen. Its negative positive charge neutralizes, and a positive charge is found over this carbon. We get this particular ion. It is called acyl cation. Acyl cation is obtained. Now this carbon is being attacked by this ethanol molecule acting as a nucleophile. A pair of electrons of oxygen is donated to this positive carbon. Now acyl cation contains carbon with a positive charge and a vacant orbital, into which the lone pair of electron is received. Then positive charge occurs over oxygen atom. The OH bond will be taken up completely by oxygen. That means the pair of electron in the OH bond will entirely go into the orbital of oxygen atom, leaving H as H positive. We get CH3 C double bond O or C2H5 plus H positive. So that is a simple mechanism for formation of ester. You need not study this, just only go through, be familiar with it, and then neglect it. Now ethyl acetate is reduced using hydrogen and palladium. So the ester is reduced using hydrogen and palladium. It is called a catalytic reduction. The CO bond breaks and HS bond breaks, and we get C2H5OH and CH3CHO. This is an aldehyde called acetaldehyde. Now acetaldehyde can undergo further reduction with hydrogen. HH bond breaks and the CO bond polarizes or breaks, and then H goes to this carbon and this oxygen. We get CH2OH. The bond is getting saturated. The pi bond is getting broken. Two valencies are created over this carbon and oxygen. HS bond is broken. The valency of H combines with the valency of O, producing OH. The valency of H combines with the valency of carbon, producing CH bond. So this CH becomes CH2. We get the corresponding primary alcohol. So acid is first converted to its ester, then reduced using hydrogen and palladium to produce the corresponding alcohol. So direct reduction of acid using lithium aluminum hydride is possible, but it is expensive. So we use another method, conversion to ester and then reduction using hydrogen and palladium. But if you are asked to convert an acid to alcohol, then you can use this step involving a reduction using lithium aluminum hydride. Now this is a commercial method. Then formation of alcohols, various types of alcohols from Grignard reagent. Grignard reagent is alkyl magnesium halide, generally CH3MgBr or CH3MgCl, or any alkyl group, any halogen connected to magnesium form a Grignard reagent. Now a primary alcohol may be produced by the reaction between Grignard reagent and formaldehyde. So addition of Grignard reagent to formaldehyde, the carbonyl group of formaldehyde adds to the Grignard reagent, and there magnesium is the positive ion or positive part, halide is the negative part, and alkyl group is the negative part, because magnesium is less electronegative than carbon and again less electronegative than chlorine. So magnesium carries a positive charge, positive oxidation state, and carbon and chlorine carries negative oxidation states, so that when CO bond polarizes as C positive and O negative, the negative part goes to the carbon which is positive. So CH3 bonds with this carbon. So we get CS3 bonded to this carbon containing 2H atoms, that is CS2. Then O bonds to NgCl, ONgCl is formed, that is the addition product of Grignard reagent to formaldehyde. Then this addition product is hydrolyzed using dilute acid. So we can write H positive and H2O, indicating acid hydrolysis in aqueous medium, that is dilute acid hydrolysis. Now there again, this magnesium is the positive part, oxygen is the negative part, and Cl is the negative part. And OMG bond breaks. H breaks into H positive and OH negative. And here O negative and Mg positive. So O negative combines with H positive of water, and Mg positive combines with OH negative of water. So we get CS3 CS2O negative plus H positive, that is CS3 CS2OH, and the other product formed is MgOHCl. Now we can convert CS3OH to CS3 CS2OH by this method. So the CS2OH group formed here is obtained from formaldehyde. So formaldehyde is responsible for the formation of primary alcoholic group, that is CS2OH. So here CS3OH is converted to CS3 CS2OH, and this CS2OH group is obtained from formaldehyde. So we start from CS3OH, which is reacted with PCl5. The OH is replaced by Cl. Then you prepare the corresponding Grignard reagent by reaction with magnesium in ether. We get CS3MgCl. Then CS3MgCl is reacted with formaldehyde. Addition of CS3MgCl to formaldehyde. The alkyl part being negative goes to carbon, and MgCl part being positive goes to oxygen. We get CS3, then CS2 from formaldehyde part, OMgCl. Then that on hydrolysis, O negative and Mg positive, H positive connects to O negative and OH negative connects to Mg positive, that is hydrolysis catalyzed by acid. We get CS3 CS2OH plus MgOHCl. So we get the higher formula of methanol. Previously we have seen the method where the Cl was reacted, the alkyl halide was reacted with the potassium cyanide to get CS3CN, and then the CS3CN was hydrolyzed to CS3COOH, and then the CS3COOH was reduced using lithium aluminum hydride to CS3CS2OH. So various methods are there for conversion of CS3OH to CS3CS2OH, the next higher formula. So conversion reactions are very helpful in studying organic chemistry, because you go through various reactions and it is quite interesting also. So do as many conversions as possible, study as many conversions as possible to study organic chemistry easily. Now, if an aldehyde other than formaldehyde is treated with Grignard reagents followed by hydrolysis with dilute acid, the product is a secondary alcohol. So if formaldehyde is used with the Grignard reagent, we always get a primary alcohol, where the primary alcoholic group results from formaldehyde, that is CS2 double bond O. Now if you use any aldehyde other than formaldehyde, we always get a secondary alcohol. Now the reaction is similar. We take CS3CHO, that is acetaldehyde, and react it with the methyl magnesium bromide. The methyl part getting connected to carbon of the C double bond O system. Then we get OMGBr. So CS3CH, then CS3 connected to this carbon, CH, OMGBr, and this on hydrolysis, CS3CH, CS3, OMGBr. The H positive part goes to O negative part. We get CS3CH, CS3OH, and MgBrOH. So CS3CHOH, CS3, that is 2-propanol is the product. It is a secondary alcohol, and secondary alcohol contain the common group CHOH with the 2 valencies connect to alkyl group. Now, how will you prepare this secondary alcohol? There are 2 alkyl group, that is isopropyl group, and this is ethyl group. Now you have to select an aldehyde from this structure. You can select CS3CS2CHO and then CS3CH, CS3MgBr. That is one choice. Then we can select CS3CH, CS3CHO, and that is aldehyde, and then CS3CS2MgBr, that is the Grignard reagent. So 2 methods are there for obtaining this compound. First you select CS3CH, CS3CHO, CS3CH, CS3CHO. Then the other alkyl part is taken as the Grignard reagent part, CS3CS2MgBr. Then addition as usual, so that this CS3CS2 part gets connected to this carbon, oxygen connects to MgBr. We get CS3CH, that is CS3CH, CH connected to CS2CH3, CH connected to CS2CH3, then O connected to MgBr, OMgBr. Then this on hydrolysis, HOH addition, oxygen connects to H positive, MgBr connects to OH negative. You get CS3CH, CS3, CHOH, CS2CH3. That is method 1. Then I have told you the second method. You start with the aldehyde CS3CS2CHO. Then this part becomes the alkyl part of the Grignard reagent. So starting from CS3CS2CHO, CS3CS2CHO, then the isopropyl magnesium bromide, CS3CH, This is isopropyl group, so this compound may be called isopropyl magnesium bromide. Then this isopropyl group as a whole gets connected to this carbon of the aldehyde group, and oxygen connects to MgBr. So we have the addition product as CS3CS2CH, CS3CS2CH connected to this carbon, that is CH. Then this CH is connected to CS3 and CS3, so CS3 and CS3, and oxygen connected to MgBr. So that is the addition product. Then hydrolysis, O negative connects to H positive, Mg positive connects to OH, and you get this product. Now one speciality of this product is that this carbon is asymmetric, because we have an H group, OH group, ethyl group, and isopropyl group. So this asymmetry is created by the addition of Grignard reagents. So the 2 isomeric products are possible. Now which will predominate, that will depend upon the stereochemistry of this aldehyde and also the bulky nature of this group. So we need not worry about the stereochemistry now. You understand that the product is possible by 2 different methods. Now ketone. So ketones and aldehydes are related compounds because both contain the C double bond O group in common. that is called the carbonyl group. Now aldehydes on reaction, if formaldehyde is taken, then we get the primary alcohol, then an aldehyde other than formaldehyde gives a secondary alcohol, and if a ketone is taken and reacted with the Grignard reagent, we get a tertiary alcohol. You take acetone and methyl magnesium bromide. As usual, addition occurs, methyl group getting connected to the carbonyl carbon. So the CH3 part getting connected to carbon, then OMGBr, ether medium, so you get C connected to OMGBr, then there are 3 CH3 groups, then followed by acid hydrolysis, O connecting to H positive and Mg, we are connecting to OH. We get CH3, 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 COH, that is tertiary alcohol. So ketone generally reacts with any Grignard reagent to produce a tertiary alcohol, and tertiary alcoholic group is COH with 3 valencies. Now these valencies are joined to alkyl groups. Now suppose you are asked to prepare a tertiary alcohol. That is CH3, then CH3, and CH2, CH3, OH. Then you mark the COH grouping around it. Then you can take a ketone whose alkyl groups are this one and this one, or this one and this one, or this one and this one. So various possibilities are there. Suppose you are selecting these two as the alkyl groups of the ketone structure, then we have CH3C, then bonded to CH, and there two CH3 groups, these two connected to the carbon, then you take this Cl group. So you have used so much portion of the molecule, then the remaining is the alkyl group only. So you take CH3, CH2, MgBr. So this is one possibility. Then as usual addition occurs, O minus and C positive, then this portion splits into so much negative and so much positive. Now this negative part goes to this carbon, so we can say this portion connects, and MgBr goes to oxygen, and the product will be CH3, C, CH, CH3, CH3, and this CH2 group gets connected to this carbon, so CH2, then CH3 is there, and this carbon is connected to OMGBr. Now in the next step, that is hydrolysis, acid hydrolysis, this OMGBr bond breaks, NH and OH group splits, oxygen gets connected to H positive, and MgBr positive connects to OH, and you get the product as CH3, C, CH2, CH3, then CH, CH3 and CH3 OH plus of course MgBrOH. Now we have arrived at the starting product, that is carbon connected to OH. This carbon is tertiary because it is bonded directly to 3 other carbons. Now one alkyl loop is a methyl loop, this one. The second one is an isopropyl loop, that is this one. And the third one is an ethyl loop, that is this looping. So that is one method. You can select the ketone as containing this alkyl and this alkyl, so that you take CH3MgBr, that is another possibility. Or you can take the ketone as CH3CO, CH2CH3, and then this alkyl part is remaining, that is taken as the Grignard reagent. So 3 different possibilities are there. You can try it and be familiar with the equations. That is enough. Thank you.